Welcome to APA's weekly webinar. My name is Billy Zadek, Stands and Codes Administrator for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted on the APA website later this afternoon, and a follow-up email will be issued to you as a reference on where to locate the session. Professional Continuing Education and AIA CLU credits are being offered for today's program. If you are an AIA professional requiring a certificate, please send an email to me at billie@apa.org, along with your AIA membership number if you have not done so in the past. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by one of our presenters. Before we begin today's session, allow me to remind you that the APA Virtual Facility Summit is open for registration until July 31st. We are bringing together experts from across the community to share best practices and critical programming. Although those fully registered by July 31st will be eligible for various professional credits as well as content access until October 9th. For the latest information, visit us at APA, www.apa.org today. At this time, it's my pleasure to turn this over to Owen and Scott. Gentlemen, take it away.
Thank you, Billy, and thank you for participating today. I'd just like to make a quick introduction. I am Scott Smith. I work for OSI Soft, and we'll just be giving an introduction to some considerations to data that you should think about when driving towards these operational intelligence initiatives that we'll talk about today with University of Maryland. Owen O'Driscoll is with us, and he is from DSA, who help support and operate the systems that we'll be talking about at the University of Maryland, as well as do the operational intelligence projects to drive forward. Again, just to reiterate the learning objectives, again, it is to talk about the individual use cases and objectives that the university knows that they need and how to drive forward. And really what we'll focus on is how that comes out from the unknown priorities that the data actually will unlock for you. We'll identify the difference between situational awareness and operational intelligence, and not least and very important, security. So how from an IT-OT integration can we drive value? And then lastly, about integration of real-time data with geospatial platforms. To start with, I really want to set the framework for data and driving these initiatives. And the reality is at the center of everyone's campus and world is really these data sources. And these can be the various building automation systems, plant SCADA systems, power distribution or other distribution systems, metering systems, renewable energy, EV charging. There's just a lot of operational data created. And the struggle or the challenge that we're going to talk about is we all have these initiatives. They can be condition-based maintenance, fault detection and diagnostics, sustainability. But how do you move from the raw data to those operational intelligence projects? And so there are 6 things that I think we need to think about in context of that as you decide to take your projects forward. 5 here. One is really the collection of data, and this sounds simple, but for the years that I've been doing this, you know, campuses, have a lot of disparate systems. They have a lot of legacy systems. You do not change or upgrade your SCADA systems on boilers and turbines at all times. So you have some systems that could be 10 or 15 years old you still need access to, as well as IoT sensors for the future. Again, what IT may not fully appreciate is the difference of time series and real-time data and how the operational will generate a massive amounts of data and how to manage that data for these processes. I think when you go forward in picking platforms and solutions, one is really making sure you have an analytics package that's built in so that you're able to use that data in real time, from metering to asset optimization, that you're able to deliver the data and the value to your existing systems. You can't replace everything that you already have. If you have a work management, asset management, you may have a bunch of tools, and you need to make sure whatever you drive forward on has a great integration strategy. But last is, as we have some of these legacy systems, we do need good ways of visualization of this data, making sure that it's accessed on devices, in the web, it's in our Excel reports and things like that. So those are the first 5, but certainly not the most important thing you should consider. I think security is definitely one of the major considerations. Historically, our security models around, especially plant systems, are what I call the castle and moat model. We put high walls and great distance between those plant systems and the rest of the campus and users. And that was great, really early in the stage of this. But as we've had greater access for data, those walls have started to deteriorate. We outsource more today. So third parties have access to this, and we do energy reporting and things. And so the new security model is we're going to continue to get data out of these systems for these operational intelligence projects, is really thinking about how you want to separate data from control. The vast majority of people will never really have a need to have access to control that need the data for these operational intelligence. And so making sure when we go through this process, and we'll talk a lot about that today as well, is having a good security platform. So let's talk about how this applies to University of Maryland. So this is the College Park campus. And I think the 3 things that I want to talk about before I introduce Owen is, I think, 3 perfect scenarios that kind of came into need. I think one, to understand the campus, is they do outsource the central plant that's power generation, chilled water, steam, which is a very common practice today. So how is the employees of the university that are, at the end of the day, still responsible for the facilities, have visibility into their outsourced provider? So they really needed secure remote access to the plant data so that they could make sure that there was a reliable level of service and they could understand the impact or implications of events that occur. Second, University of Maryland did run a legacy system, SciTech, and they weren't replacing that, but they really wanted the data access. So they were looking for a data provider that could make sure they had that legacy access. And so they have new systems, they have new Shark ion meters, they have Modbus, they have all kinds of different technologies, but SciTech is a core of their campus and making sure they have access. And then third, tied really to the first, is as we do look at outsourcing as a solution out there, it's not just throwing it over the fence under a performance contract, saying you perform this much, give me this energy, and I pay this fixed rate. In reality, the buildings impact the plant impacts the buildings, holding people accountable from good maintenance structures. You know, as a campus, when you outsource, you really give them an N+X highly available system that you've built and maintained for years, and you want to make sure that they protect your assets. So having a good ability to monitor your outsourced provider is another thing that I think came up at University of Maryland. But with that said, that's the framework of our discussion. We'll start with Maryland, and I want to turn it over to Owen here to really talk about the project. Owen?
Thank you, Scott. So just a quick introduction. My name is Owen O'Driscoll. I'm the practice lead for critical infrastructure protection at DSA, and DSA is an employee-owned IT consultancy company headquartered out of Trevose, Pennsylvania. And within critical infrastructure protection, we focus on data-driven solutions that improve the resilience and effectiveness of critical systems. And one of our notable customers is the Nuclear Regulatory Commission, the NRC, where we have operated and maintained the emergency response data system for over 12 years now. And that system, called ERDS, requires collection and integration of data from each of the 96 commercial reactors across the U.S. to a central platform, and it's a project that we're very proud of at DSA. My personal background, I'm a mechanical engineer, graduate of Trinity College Dublin in Ireland, and I completed a PhD with Johnson & Johnson with research that focused on the application of machine learning to improve the energy performance of large facilities. I'm a PE licensed in Virginia, and over the last 10 years, I've worked in energy engineering, utilities, and facilities roles at companies ranging from very small consultancy firms to multinationals like J&J, Siemens, and Diageo. So Scott's already introduced the learning objectives, and to reiterate a little, my goal for the webinar is to use actual applications and use cases to demonstrate some of the ways the University of Maryland has improved situational awareness and operational transparency. And one shift is that at the end of the webinar, we're going to spend 5 minutes or so going through the role data will play as schools and offices look to reopen in fall after the coronavirus pandemic, or hopefully after the coronavirus pandemic. So that's not something we initially planned to cover when we submit the abstract for the webinar, but maximizing campus safety is definitely and obviously critical. So we're going to introduce some monitoring-based ideas that can possibly help support that goal. Okay, so this slide here is really going to be the foundation for everything we'll go through on the webinar, and it introduces our approach to situational awareness and operational intelligence with the inclusion of cybersecurity monitoring. So starting on the left-hand side, it's a lot of the typical systems you'll see on a large multi-building campus. So we have metering systems, control systems. So here, this could be a SCADA for a central plant, or it could be a building automation system on the demand side or building side. We've got assets that maybe aren't integrated, large generators, maybe lift stations, sump pumps, things like that. Diagnostic systems, vibration is a good example here. There's facilities and utilities databases, so maintenance management, asset management as examples. And then finally, geospatial information systems. So what we do is collect the critical data from all those systems, and Scott touched on this before. There's a lot to that, lots of different protocols, lots of different data transmission pathways, but we collect all that data and bring it to a central operational data warehouse. And that's really where we claim to have situational awareness. So now we had disparate systems, we bring all that information together, we can look at it in real time at the same time. So that's the situational awareness piece. And then building on top of that, we layer analytics. And that's what you can see in the calculate column here. And the analytics, it's the full spectrum. So starting with the very simple things like fault detection, so logic-based rules that I'll come back to, comparisons against industry best practices, and then it really goes all the way through to much more sophisticated approaches, things like neural networks, genetic algorithms, and other really advanced machine learning approaches. And at that point, when you've paired your analytics on top of situational awareness, that's when you get to operational intelligence, and the visualization and sort of alerts and notifications that go with that intelligence are what we have in the second to last column, where we talk about dashboards and incident response and things that we'll get to during the webinar. And then finally, on the right-hand side, it's really the value propositions or the use cases. So condition-based maintenance, fault detection, load management, and some of maybe the other buzzwords that you're familiar with. And the bottom bar then is maybe where this is a little different. So it's continuous cybersecurity monitoring. And that allows us to constantly assess the status of each server that hosts a facilities or utility system. So here we're looking for things like the latest software versions being installed, all the recommended patches being installed, are all of the communicating ports being managed correctly. And we also need to, and Scott touched on this again, we need to understand the safest way to connect different networks based on their criticality. So we need to decide if it's okay to have a firewall exception, or maybe we need something that's much more secure, and maybe it's hardware based, something like a data diode. And answering those questions is what allows us to manage the risk profile of this new integrated and smart facilities infrastructure. So the real key takeaway there is that there's a lot of systems, there's lots of data, and there's typically very little integration. But using a data infrastructure solution, it allows end users to get all that data in one place, and that one new operational data warehouse then becomes the foundation upon which all of your data-driven initiatives get built upon, and that's what we'll go through in the webinar. And before we get there, this is just really to reiterate, because they are learning objectives of the webinar. Just going through before to double down on what the differences are here between situational awareness and operational intelligence. So in the most simple terms, situational awareness is really system integration, and operational intelligence is analytics, or what analytics give you. So the outcomes for situational awareness: data access and real-time operational insights, and they're very different than operational intelligence, where the outcomes are much more value-based, so risk mitigation, efficiency, and resilience. All right, so now we'll go to the actual applications and use cases at Maryland. So the first one I want to introduce is related to electrical distribution across the College Park campus. The image I've got here is just a standard electrical one line, and the reason I included it is to make maybe the obvious point that electrical distribution across a large campus is complicated, and important data lives in lots of different systems. So we have on the left-hand side PDUs, or power distribution units. They've got their own monitoring systems. The SCADA system at Maryland houses the data for power generation. When we get to the UPSs and ACSs, sometimes they live in the building automation system. And then finally, there's standalone power monitoring systems that contain all that metering and sub-metering and power quality data. So the disparate sources, that lack of real-time insights into these isolated systems was a challenge that College Park was facing. And that challenge was really magnified by the fact that they didn't have any remote monitoring capabilities for many of these systems when they had a grid outage back in 2016. So in total, the grid was down. So the grid connection was down for maybe 90 minutes, but the university itself ended up being down for an additional 2 hours. And that was because they didn't have complete transparency into the distribution of electricity across College Park. So we worked with the university, deployed the PI system, and the next 3 slides are going to go through what this maybe confusing slide looks like in practice today. The first screen here is the operational status of distribution across the entire campus. So this includes primary grid feeders on the top, the CHP feeds on the bottom, and then each of the primary cubicles in between. So what we've done in this one screen is take that complicated one-line diagram from the previous slide and distilled it into a really simple screen with traffic light color coding that allows system operators to really quickly assess the status of the entire campus. And going back to the definition from a couple of minutes ago, this really is situational awareness. Everything that you see here, it's real time, and the screen is interactive. So when a user wants to get more information about an individual feeder or a cubicle, they can just click on a feeder and it will bring them to the next layer down. So getting more insight, more transparency. And that's what the next slide is going to show. So now we're at the feeder level. So now it's the real-time status of each building. And it's still situational awareness, but now if an electrical outage occurs, we have analytics and notifications built in here to immediately notify all of the appropriate utilities and engineering stakeholders. So the layering of analytics, or the addition of analytics on top of situational awareness, and the ability to immediately communicate specific information to different stakeholder groups advances situational awareness to operational intelligence. And before this system was installed, one of the most time-consuming tasks, and this is the case for really anywhere that doesn't have an outage management system, one of the most time-consuming parts of this troubleshooting aspect is getting the information from people in the field. So what buildings have power, what buildings don't, and then communicating this information to the appropriate people, and it can take a lot of time. So with what's installed now at College Park, all of that data gathering and the communication, it's automatically handled, and this gives the rapid response team a head start restoring power, and that's the most important thing. The smartphone is just included here to illustrate some additional, capabilities of this application, and that is that it's all accessible from any smart device. So now when engineers are in the field at College Park, if they make a change, so let's say move a switch or change an open point, they can immediately reflect that change using their smartphone, and the system is up to date. And that takes care of a lot of the pen and paper stuff and maybe losing the paper on the way back to the office or anything that may happen. So it's just all real time. And then the final step, so from campus to feeder, the final step is within a building. So the level of insight and transparency continues. And now we're inside an individual building. So we've got real-time information on the status of the grid connection, obviously very important, the availability of emergency generator power, and the status of the automatic transfer switches and the uninterruptible power supply. And again, this is great information to have. Maybe it's not a screen you want to look at a lot, but what we have is analytics that will immediately notify people if a generator isn't online for some reason, if there's a switch in the wrong position, or if UPS battery life has gone below a certain threshold. And this end-to-end transparency, so from the first screen to where we are now, this transparency has really improved the university's ability to respond to outages, and it has significantly reduced the downtime that they experience when an outage does occur. The next example, so that's the electric piece. The next example then, sort of a further step in the integration here, is going to look at chilled water and the integration with a geospatial platform. So what you're looking at on this screen now is just a standard engineering design drawing. This one is for the distribution of chilled water across a small portion of College Park. So each building has the design information for pressure drop, for flow, for delta T. But as we're all aware, the design data rarely, if ever, is representative of what actually happens. And this was a challenge that they were facing at Maryland too. So the question became, how do we operationalize a drawing like this, make it digital, and then provide real-time situational awareness into the operation, and not just the operation, but the performance of the chilled water system. And this is what we came up with. So this is now, this visual includes data taken from multiple different systems. So we have the SCADA system that controls the operation of the chilled water plant, and then multiple automation systems that control different valves connected to the chilled water system and air handlers, et cetera, et cetera. And it's all overlaid on this Esri map, and it's all real time. So this type of visualization, at least in my opinion, is definitely a step change from what's available or has been available to facility managers when it comes to chilled water distribution. And before this integration at College Park, if an engineer wanted to do sort of we'll call it an assessment that needed chiller data and building data, they had to go to multiple systems, download trend files, maybe bring them to Excel, make sure all the timestamps line up, and then maybe after a few painful hours, they can start doing some data analysis. But all of that data manipulation takes time, right? It's tedious, it's frustrating, but mainly it takes time. So with the system like this, that's all taken care of, and you get the data from all systems in the format that you want it in without any sort of data cleansing or scrubbing. And one story I like to tell on this this application, this use case, is the first time we presented it at College Park. So we're sitting in a meeting room and we're going through screens, and this one comes up, and the facility manager sort of a little abruptly interrupts and says, "Is this live, or is this demo data, or sort of what's going on here?" And once we said this is in fact live, the gentleman had to leave the room because there was an issue with one of the loops that they weren't aware of. and not a serious issue, but an issue. And I think that, to me, really just summarizes the value of an integration like this. And that is that obtaining holistic situational awareness with centralized data is really the only way that you can accurately assess and monitor and evaluate a large system like this, the operation of a large system like this. And much like the electrical screens, this is sort of like the landing page, but we can move between different screens now. So there's that interaction. And the next slide I show is going to be what happens when you click on an individual building. So again, you're getting more insight and there's more transparency. And that's what we can see here. So now we've moved from that high level overview, and now we're at a template screen. And the template screen certainly won't dwell on it, but the way it works is the data within the system is all in a very structured format. So when it comes to building visualizations, you build one visualization and then the data is automatically funneled into screens that you've built. So you don't have to build 100 screens like this. You just build one, and because you've got the structured data, it populates it. But what you can see on this screen is the information you'd want. So you're looking at chilled water consumption for a building. You've got temperatures, valve positions, flow rate, and consumption. No new data here, right? Everybody listening could probably make a screen like this, maybe could make a screen like this using a system they have. So this is still squarely situational awareness. What we want to do now is move towards operational intelligence, and for that we're using analytics like we have before. So if we continue to use this example, we know that there's a correlation between chilled water consumption, temperature, and humidity, and wet bulb temperature. So what we do is we have models built within the PI system that automatically update, and then as time moves forward, we have a model of expected performance and we have actual performance. We compare the two, and then we create an alert if there's a non-standard event. So if consumption, let's say right now it's 75 degrees, 54%, and we're 330 tons, we have a model. So let's say that goes to 380 or 390, we're immediately notified. Okay, so obviously there's a lot in those models, and we need to make sure that the level of correlation is appropriate. So there's more to it than just saying we turn it on and it goes. But once the correlation does exist, we do just turn it on and it does just go, and it works. So that's the chilled water piece. The next application then is going to be classroom scheduling at College Park, and how integrating systems that you maybe already have access to but just aren't connected can have a tremendous impact on your sort of energy and cost spend related to HVAC. So as the little bit of background here, over the last maybe 8 to 10 years, I've done a lot of Azure A2 audits, maybe more than I'd like, and 95% of the time in the reports I create, there's a recommendation to improve scheduling. And the reason that's in almost every report is because the most common approach to HVAC scheduling, and the approach that was in place at Maryland, is still to manually enter schedules within the BAS to cover, sort of in inverted commas, normal business hours. And the obvious issue here is that program schedule is really covering worst case scenario, but it's not accounting for the actual schedule of an individual space. And there's good reason for that. It's really difficult to make sure that you're always keeping every single space up to date manually. It takes a lot of time. It's not really practical. But at College Park, they use cloud-hosted room reservation systems. So things like Google Calendar, 25 Live, and that's where the professors themselves interact. They say when they're going to be teaching English 8 to 10 Mondays for however long, and that information lives in a system that people maintain, students interact with, but that's the actual scheduling information for these classrooms. So it exists, but it's caught in this IT silo that isn't connected at all to your OT, your operational technology systems, and really specifically your building automation system. And the true definition of a smart building, well, part of it at least, is making that connection between IT and OT and bridging this gap. By bridging the gap you can see here, we were able to automatically update HVAC schedules based on the information stored within the online room reservation systems. So this is just sort of filling in the gaps. So we tie directly to the SQL table, so where the data is stored in those room reservation systems. We tie directly in there, we bring the data through to the system, and then we send signals to the automation system that feed into the control logic and then impact change at the terminal box level. So this is one really powerful example of how connecting systems, and really it's systems that you already, at least at College Park, right? They already had these online calendars. They already had an automation system. And by joining the dots, there's just a really big impact in operations and energy and cost spend and savings. And that's what I'll just show here quickly. So this is a little bit of a grainy image taken out of the ALC platform. It's just raw data for electricity consumption for a building where we deployed this. And you'll see an immediate step change from when this was deployed. So at a minimum, we're seeing 30% HVAC energy savings, and it isn't in place a full year, so there's still some M&V left to do, but this is pretty much typical of what we see for the buildings that we've deployed the scheduling project at. And then the last bullet point I have is that this approach has been approved by the local utilities, and that's for electricity and gas. So this is an electricity power profile, but the approach itself saves not just electricity, also natural gas. And now this approach has been rubber stamped by the local utilities for incentives and rebates, and that's really pushed this integration into a very positive place from a simple payback return on investment standpoint. It's below 24 months at College Park. So definitely not just something that makes sense because you're bridging the gap, but also has that payback and really does help the bottom line. Okay, then the last application at the University of Maryland then I wanted to talk through is fault detection. And FDD is something I'm sure at least most people online have heard or encountered. It's definitely, I would say it's the most popular data-driven facilities optimization methodology out there. And because it's so popular, over the last maybe 10 years or so, there's now just huge libraries with thousands of different rules, and there's almost no standardization around what FDD should look like. And at a previous job, I spent some time designing and deploying FDD projects. And the number one piece of information that I shared with the University of Maryland, and I'll share now here, is that just because there are 100 or 1,000 or 10,000 rules available, it doesn't mean that you should deploy them. And I would take that one big step further and say, you absolutely shouldn't deploy hundreds or thousands of rules. There's no return on that investment. So your initial system design, so how you originally deploy FDD, how it's going to fit into your existing maintenance practices, they're much more important decisions and conversations than how many rules you're going to apply. So if let's say you apply 10 rules across a campus, you find 100 faults a day for a large campus, and that's extremely low. It would be a lot higher. But how do those faults get communicated to your engineering staff? And if they do get communicated, do you have 5 or 10 people sitting around somewhere who are just waiting for what gets pumped out of the FDD system? And the answer for almost everyone, and probably everyone, to that question is no. So how do you integrate FDD into your existing workflows? And the most effective approach there is a phased deployment, and you want to focus on high impact, high probability faults and deploy them campus wide. And that's based on a lot of sort of, I guess, guidance, industry guidance, and also my personal experience. And I would say that there's a small subset of fault detection rules, and this is true for air handlers, it's true for chillers, for boilers, but a small subset of the rules deliver 80% or more of the value. And going to the slide that's on screen here, it's a standard air handling unit. So there are definitely many hundred rules we could find in different libraries online, but there's really only 20 or 25 that are truly valuable and that you would want continuously running on your equipment. And going through the list we have here, I mean, an obvious couple of good rules. So let's say economizer. Economizer, everybody should be looking at the operation of economizers, and that's because if an economizer gets stuck open in summertime, number one, it's very expensive, but number two, the machine, the chiller, the capacity of the coils isn't designed to cool air at the summer design point at 100% outside air. So it's just going to be very uncomfortable in your buildings. And then the flip side is, if it's 100% closed, then maybe that's a safety issue because maybe there's no ventilation. So maybe 100% closed is truly closed, and it's not 100% closed is minimum open. So there could be a safety issue there. And I'll come back to outside air when we do get to the coronavirus, the sort of section at the end. Next obvious rule that you'd want included, and I think that's a good point. I think when they're obvious, it means that they probably should be in place. So simultaneous heating and cooling doesn't need a lot of explaining. In some cases, simultaneous heating and cooling does make sense, but you can program those out very easily. And the vast majority of times, you don't want to have your cooling coil and your heating coil open at the same time. So they're pretty clear examples of what I would call high impact rules that you would want to apply or deploy across a campus, but there's a lot more that should be avoided. And one example, again, looking at an air handler like this would be, if you want to look at your supply air temperature versus your supply air temperature set point and have a fault if it's a 2-degree deviation. So if you're more than 2 degrees away from that set point. And that's a rule that's in a lot of systems. It's a rule that was in a system I've worked on. And you really have to step back and ask, is it valuable? All right, so if we go through that analytic and think about it, the instruments, so the temperature probes in an air handler, when they're installed, are probably accurate to plus or minus a degree, maybe even 2 degrees. And they drift over time too. So the perfect out the box one goes in plus or minus a degree and a half, we'll say. And what that means is that with that plus or minus 2 degrees, there's a likelihood, not a strong chance, a likelihood that you're creating faults that reflect the accuracy of a sensor and not the true operation of your system. But then even if the sensors were accurate to 0.1 of a degree, which they're not, but if they were, do you really think, or do you really want to ask somebody to go troubleshoot why the supply air temperature at this air handler is 57 instead of 55, right? So is that a fault? And that's all part of that initial design. But I think the answer to that question is squarely no, that you don't want to ask somebody to do that or to troubleshoot that because there's nothing to troubleshoot. So what's clear is that applying too many rules results in just tremendous amounts of faults, and that reduces the overall effectiveness of your fault detection system. And the best way to make fault detection work is to go, and this is what we've done at Maryland, so the best way to make it work is to go with a few high impact rules that cut back on all the noise in the system, and that's how you really get to the value of FDD. And then building on top of that by using a data infrastructure, that centralized data warehouse, you can integrate with other systems and start to investigate and explore closing the loop. And what closing the loop means is you want to integrate your fault detection analytics with your maintenance management system so that you can automatically generate work orders or tickets in your maintenance management system based off of the algorithms that are running in the fault detection side. So I would say that is something that's clearly very powerful, but it's certainly only advisable for those extremely high probability faults. and not for everything you have in your fault detection system. And that's the last data-driven application, the last College Park, Maryland-focused application I wanted to talk through. But we did want to spend a few minutes just going through some of the recent developments with coronavirus, and again, talk to how monitoring and the different systems we have access to may be able to support some safer school openings. And to introduce that, this is just a very brief timeline of how the facilities community has reacted to coronavirus. And these are just highlights. There's a lot of studies almost every day, and I just picked out the real high points. So starting with right around March 11th, when schools did begin to close, go online, was right around the pandemic declaration was made. And pretty soon after, ASRE established the epidemic task force, and those guys have been working real hard. There's almost weekly updates coming out and new guidance. And one of the earliest things that they said was that around April 14th is that HVAC professionals are going to play a role. All right, so it's unclear how big a role, but they are going to play a role. I don't have anything sort of highlighted in May and June because it was literally every day updates, and it sort of continued that way. But then right around July 7th, there was encouragement from the White House to reopen schools in fall. And then the very next day, a study was published in an infectious diseases journal that basically said the scientists, 239 scientists, and all of the people who work for those principal investigators, that coronavirus may be airborne, and it was at least time to start taking that more seriously. And then just last week, ASRE published a brand new infographic online, and I'm not sure if everybody's seen it. If you haven't, I highly recommend you go see it. It's got a lot of excellent information in it, and it does have a lot of clear direction. But I still think where we've gotten to right now is people still have more questions than answers, and that's maybe just to be expected from where we all are, but that is the case. And what I want to focus on for the next few minutes is the gap, and there is a gap between the guidance that we're all receiving and then how buildings can actually operate. So what people are saying should be done versus what can actually be done, and they're not the same thing. So I think, to put it bluntly, some of the recommendations maybe aren't practical, and to put a very fine tip on it, some are impossible. And that's sort of what I want to just touch on briefly. No answers, really just perspectives, and that's what I want to spend the last few minutes doing. So one thing that isn't going to change is that the most effective way to reduce the spread is going to be the things we've all been doing. That's social distancing, it's wearing masks, it's surface cleaning, and they're facts. But there is that growing belief that in indoor environments, air velocity can suspend virus particles and take them well beyond that 6-foot radius that people have been talking about. And there's also sort of parallel research evaluating if the virus is truly airborne and not just being sort of suspended, if it's truly airborne and can be pulled through ductwork and recirculated. Quick disclaimer before I go on. There is no conclusive proof. I'm not saying there is no conclusive proof, but organizations like ASRE have already started to issue guidance on how to operate systems in schools with that in mind. So it's not proven, it's still under investigation, but guidance is starting to come out to adjust for that eventuality. So the first thing I have on the left-hand side of this slide is an image from a university in Texas. And this is a standard classroom where they're installing plexiglass to break up that airflow. And this is definitely a proven approach, right? We see it in grocery stores and lots of other public or high occupancy spaces. But there's a lot of guidelines out there that are less clear-cut and much more difficult to enforce or put in place. So the first one I have on the top right-hand side is cleaning. So this is guidance from the Industrial Hygiene Association, and they're recommending that all HVAC intakes and returns are cleaned daily. All right, so if we take this back to College Park for a moment and think that a campus like that has probably over 2,000 air handling units. And maybe it takes 30 minutes, and maybe it takes a lot longer, right? It doesn't take less. So let's say it takes 30 minutes to clean each one. Now we're at 1,000 man hours a day, and that's enough work for 100 people working 10 hours a day, right? So that's not an option, but that's the guidance. So there's a gap there, and just walking through the other items on the right-hand side, operating hours is definitely a little more clear-cut. I think most schools will end up doing, again, inverted commas, flushing. So maybe 2 or 3 hours before buildings become occupied, they'll run pretty much wide open. And the thinking there is more air changes, cleaner air, less virus. I think not too hard to follow that one. But I do want to go into the last two I have, the filtration and ventilation, in a little more detail, and really talk about maybe some of the ways monitoring data could help schools be safer when they reopen. First, to air filtration. So this goes back to fault detection. And one of the most widespread analytics that people put in place, and I think it's a perfectly fine one, is to monitor pressure drop across an air filter. So usually when you install a MERV 7 or MERV 8 filter, which is standard, you'll get, 0.1, 0.2, in and around that range, pressure drop for a clean filter. So we bring that data, it's in an automation system, it's in a fault detection platform, wherever it is, we monitor it. And when it gets to a 1/2 inch pressure drop, a 1/2 inch of water column, then we have a dirty filter. And we want to change that filter because it's dirty. The data is telling us it's dirty. So now the guidance here is that we want to have higher efficiency filters, so MERV 13 or higher. And let's assume we can install those filters. And that is an assumption because filter racks are different width and they can't all house the same filter. So let's just assume it is going to fit. Now this MERV 13 or 14 filter goes in with a clean pressure drop of 0.3 or maybe a little more. But now that we have that information, we can continue monitoring for dirty. Maybe it's not 0.5, it's 0.6. But what we can also do is monitor that differential pressure or that pressure drop to make sure it doesn't decrease. So now we know if it goes below the pressure drop when it was installed, that there's air bypass or that the filter has been dislodged. So we're using the data we already have and we're looking at it slightly differently. And instead of looking for energy gain, there's just that safety-minded analytic to just make sure that the filter is still there and all your air is still passing through the filter as it's supposed to. The next and last piece on this is related to the guidance around ventilation. So the guide here is to keep outside air as high as possible, 100% if you can. And again, going back to FDD and how we currently monitor data, the standard way we look at economizer operation is making sure that it's not wide open in summer or that there's not a mechanical issue like a broken linkage. It's not just stuck in the same place and the 0.8% isn't changing. But the new logic will be to make sure that the outside air damper stays where in the position that you've deemed appropriate whenever the building is occupied. So that's also good guidance, I suppose. But the real challenge is that someone has to figure out how many different air handling units can go to 80%, to 90%, to 100% before you reach capacity on your chillers, right? Because that's what's going to happen. Everything can't go 100%. That's not an option. So somewhere between where we are now, which is minimal open during summertime, and what the guidance says, and I know the guidance says up to 100% if possible, but there's a lot of space between 15, 20%, and 100%. So what happens when we get to the capacity of our chiller systems? Do certain buildings get priority? And I don't know the answer, and it's going to be different for every school. I mean, is every school going to hire design engineers, tab contractors, and reevaluate and rebalance their systems before the 31st of August? I think that's extremely unlikely. And what's going to happen is it's going to fall on facilities and utilities people to figure that out. To figure that out, you've got to look at your data, the data from your chillers, the data from your air handlers, the data from your boilers in one place so you can determine what the sort of maximum is for all of the different systems because there's so much sort of interoperability between them. And I think the summary takeaway before we break for questions is just that we're all together heading into uncharted waters on this. And there's lots of questions that we need to answer, but taking advantage of the data that we already have at our fingertips is going to be an important part of safer school reopenings. And with that, I'll break for some questions.
Hey, thank you very much. One quick question. Were there some examples of issues or concerns that were not known, but the data identified?
Yeah, so I think, yeah, I mean, a lot of different issues. So I think just because it's fresh to mind, thinking about economizers, when we turn on fault detection systems, when anybody turns on a fault detection system, you almost immediately notify like things like I covered. So simultaneous heating and cooling, valves passing, outside air dampers being stuck closed. I mean, I've seen that more than once, stuck open many more times. So that's definitely the purpose of the analytics, is to uncover those unknowns. So I would say, yes, absolutely. That could be a whole webinar of things that were uncovered.
Okay, thank you.
And
someone made it, oh, go ahead, Scott.
And Owen, when they initially went in, were there any, not fault detection, but you're doing just your situational awareness? Were there other things that were more kind of highlighted? I know I've heard things on everything from lift pumps to things. I'm just wondering, what was that potential opportunity that was really unknown at that time?
Right. So maybe one example is to do with sump pumps. So they had, and maybe it wasn't immediately when we turned it on, but it addressed sort of a known, maybe it is a known issue, so maybe this isn't a good answer, but basically they had water flooding different below grade spaces, and the only way they figured it out was when someone sort of went down there maybe to look at a compressor, or maybe an air compressor stopped working. And with the system that we put in place here and monitoring how those sump pumps were operating, and how frequently they were operating, we were able to cut back on the number of significant water leak events that they had at College Park from 4 or 5, and significant being like lifting carpet, baseboards, all those fun things, from 4 or 5 a year in some spaces, right back to 0. So that's another, I think, application or value proposition of bringing that data back to one place, analyzing it, so you're not chasing your tail the whole time.
Okay, thank you. Someone wrote in and said, the logic that alarms on low filter DP must also account for the AHU being off. For sure, absolutely. That's absolutely correct. And yeah, most of the fault detection rules have multiple, and I certainly oversimplified it in the flowchart, multiple different parameters that feed into them, and making sure that the air handling unit's on and the fan is on and that there is some static pressure would definitely be important in that rule. So that's absolutely correct. Okay, well, thank you. At this time, I don't have any other questions coming in. I think you've given us all a lot to think about. So if I don't see any questions come in, I'd like to thank Scott and Owen for a great presentation. And I'd like to thank everyone attending this webinar today. Thank you so much for taking time out of your busy schedule to attend these on a weekly basis. We really appreciate it, and we want you to be safe, stay healthy, and until next week, thank you so much. Bye-bye now.